So in this video, I'm going to recap the probability rules and I'm going to give an illustrative example of how to use each rule. So to start off with though, probability can be defined as the chance a specific outcome will occur, and it's measured as a value that's between 0 and 1. So if you end up with a probability of 0, what that is telling you is that there's no chance of your specific outcome occurring. On the other end, if you have a value of 1, that means that your specific outcome will always occur. And what that means is if you have a value that's between 0 and 1, there is some chance it will occur and some chance that it won't. And that tends to be what we're interested in. Alright, so we're going to go through this example for each of the different rules. So what we've got here is a bag of marbles. You can see that they're different colors and different sizes. And what we are going to be looking at is the probability of picking some type of marble. So we'll go through each of them in a moment. What I've done though is, rather than looking at it in this kind of form, I've put it into a contingency table. So it's split up between the size of the marble, so big and small, and then the different colors of the marbles, red, blue and green, and the totals have also been tabulated. So that's what we're going to be working with. So the first definition we have is for marginal probability. So this is going to be the chance of a single outcome, and it's going to be coming from the margin of a contingency table. So this is our first example demonstrating that. So we want the chance of picking a big ball. So how we can write this is, if we say P, that's telling us the probability, and then inside the bracket we write what we want the probability of. So the general form is P of A, so the probability of event A, and in our case, event A is picking a, I'll put big ball, so I'll just put big here to make it easier. So how we're going to get this is from looking at our contingency table, and we're looking in the margin. So if we scroll back up here, alright, the margins are like these total sections. Alright, and we're interested in a big ball, so that's this one here, and the total number of big balls we have is going to be 4. And if you look at my picture, you can kind of see it, 1, 2, 3, 4. So the chance of picking a big ball is going to be the 4 divided by the total number of balls that we have to pick from, which is 14. So we can write this as the chance of picking a big ball is 4 divided by 14, and if you want, you can make that into a decimal. So 0.286 is what you get from a calculator if you do that. Again, what you can see is that we have a value that's between 0 and 1, okay? And if you want, you could convert this into a percentage. So if you did that, it would be a 28.6% chance that we would pick out a big ball from our bag of marbles. So that's the first definition for probability. So marginal just means it's a single outcome that's picked from the margin of a contingency table. Alright, so the next one here is joint probability. So this is the chance of two outcomes both occurring, and sometimes people refer to this as the intersection. So the intersection of a row and a column from your contingency table. So an example of this one would be the chance of picking a big and blue ball from your bag of marbles. Alright, so the general form of how people write this is P again for saying that it's the probability, and then it's two events occurring, and those events are defined as A and B. So in our case, event A is going to be that it's big, and event B is going to be that it's blue. This thing here is just a symbol that's used to define the intersection, okay? So this is telling you we want the intersection or the AND case, so we want both A and B to be true. So we can get this from looking at an intersection of a row and column in our contingency table. So let me just write out, so we want big and blue. So if we go back and look at our contingency table, we should be able to see how many there are. So big and blue, it's going to be this cell here. Alright, that's the intersection of a row and a column. So it's going to be 1 out of the total, which is 14. So we can write this as 1 divided by 14. And again, if you type that into a calculator, you can get a decimal representation, and it's about 0.071. Again, it's a number between 0 and 1, which is good. It's closer to 0 this time, so that means there's quite a small chance that we're going to pick out one that's both big and blue. If you convert it into a decimal, that's about 7%. And that kind of makes sense, because if we go back and look at our bag of balls, there is only one big blue one to pick from out of the total of 14. So of course it's going to be quite a small chance that we actually get that one if we pick randomly. Alright, so the next definition that we have is for a union. So this one is when we have, for two outcomes, A and B, the chance that either A or B or both are going to occur. So there's actually a formula that we can use to help us out in calculating this one. So that is the probability of event A or B or both occurring. Okay, that's what this little U thing here is. So this is the union. Alright, remembering that the union just means the chance of A or B or both occurring. So that's the notation. And we can write this as the probability of event A occurring plus the probability of event B occurring minus the probability of both A and B occurring. And remember this one here, it's like the other way around. So if it's a U, that means union. If it's the other way, this is the symbol meaning intersection, which was what we just did a moment ago. So we need the probability of A plus the probability of B. These are ones that we can get from the margins. So these are the marginal probability cases. And then minus the probability of A and B occurring, which is the intersection of those events. So let's do an example. So here we want the chance of picking a ball that is blue or big. Okay. So we can write it out using our notation. So the general form looks like this. And we're looking at A can be blue. So we can write this as the probability of it being blue. And we want the union with it also being big. So substituting this into this form. So it's the probability of it being blue plus the probability of it being big minus the probability of it being both blue and big. Okay, so this is basically just removing those items that are going to be counted twice, okay, from our contingency table. So let's go and look these up. So the probability of blue and the probability of big, that's our marginal probability cases. So looking at our contingency table, the probability of our ball being blue is going to be from the margin, so 4 divided by 14. And the probability of it being big is going to also actually be 4 divided by 14 there. So let's write those in. So 4 on 14 plus 4 on 14. And then we need to take away the intersection of it being both blue and big. And actually, this is what we did a moment ago. Just got this flipped around. It's 1 on 14. Again, if you refer back to your table, big and blue, you're looking for the intersection of them. So it's 1 divided by the total of 14. Oop, sorry, here we go. So these are fractions. If you want to, you can kind of add them together. So you get 4 plus 4 minus 1 on the top line. So that's going to be 8 minus 1, so 7. And then the denominator is the same. So 7 divided by 14. And if you wanted to express that as a decimal, it's the same as 0.5. So that would be the chance of picking a ball that is either blue or big. Okay, 50%. Alrighty, next one. Got conditional probability. So this is going to be the chance of one event occurring, which we're going to call A, conditional on another event occurring, which is B. So up until now, we haven't had any conditions on what we've been picking from. It's always just been the total number of balls in the bag. But now we've got some other condition, which we're going to be picking from. So again, there's going to be an equation that helps us out with doing this calculation. And we can write it like this. So the probability of A, then we have a line B, so this means the probability of A conditional on B is equal to the probability of A and B intersecting, remember this is the upside down U, which means intersection, divided by the probability of B just on its own. So that's the marginal probability. So you just need to watch out with the order, okay? This is the probability of A conditional on B. So this is the condition. You need to be in the right order, otherwise you're going to get the wrong one on the bottom line when you go to do the calculation. Okay, so let's do an example. So we're looking here for the chance of picking a big ball given that the ball is blue. So given that the ball is blue is the part that's telling you the condition. Okay, so when we write this out in our mathematical notation, we need to make sure that the blue condition is the second one here. Okay, so we're looking for the probability of picking a big ball conditional on it being blue. And we can put that in here. Right. So we've already done this one before. This is the intersection of big and blue. Okay, so scrolling back up. The intersection of big and blue was the 1 divided by the total that we have to pick from, which is 14. And then on the bottom line, we just want the probability of it being blue. So that's the marginal probability. So that's going to be the 4 divided by 14. So if we go back and substitute that into our equation, what we've got is the 1 on 14 divided by the 4 on 14, sorry. Alright, so to simplify this, I'm going to do it a bit longhand this first time. So if you wanted to, you could write this as 1 on 14 over 4 on 14 like this. And remember that like dividing fractions is the same as multiplying by the reciprocal. So you can write this as the 1 on 14 multiplied by, reciprocal means flip this over, so 14 on 4. So what we're going to find is that the 14s then cancel top and bottom line, and you're left with 1 on 4 as being the answer. Okay, if you wanted to, you could then write this as a decimal, which would be 0.25. Now what you're going to find is that each time you do this, basically you're going to get the same denominator on both of your fractions. So every time these are going to end up cancelling. So you can just kind of directly go to this being equal to 1 on 4, or in this case 0.25 as well. Alright, so what this is kind of telling us is if we go back and look at our bag of marbles, what we're probably going to find is that there is one big blue ball out of a total of 4 blue balls. So let's go back up and check that out. Okay, so the condition was that we've got a blue ball. So that kind of just leaves us with these 4 options, which is why we ended up with the 4 on the bottom line. And only one of those is big. Okay, which is why we ended up with the 1 on the top line. So that's kind of what your conditional probability is looking at, is you have a condition, which just kind of brings you back to just having that set of, I guess, marbles in our case. And then it's just the probability of picking one type of it, so the big ones that we just looked at. So we're going to do a second example now of this conditional probability stuff. So here it is. So we're looking at the chance of picking a red ball given the ball is small. So again, we need to make sure we pick up correctly on which one is the condition. And this time the condition is going to be that the ball is small. Okay, that's fixed, non-negotiable. What could change is what color we end up picking. So that's our condition. So if we want to write this out, we want the probability of the event, of it being red, conditional on it being small. So that's why it's the second one in this notation. And we can write it out as being the intersection of it red and small divided by the probability of it being small. So we need to go back and look up these 2 events. So red and small and just small on its own. So back up here. So the probability of being red and small is the intersection here of 5, and that's out of the total of 14. So that's going to be our numerator. And then the denominator was the probability of it being small. So that will be looking at the marginal probability of small, which is going to be 10 divided by 14. Alright, 5 and 10. So coming back down. So the top line is going to be 5 on 14. The bottom line here was 10 on 14. Again, we find that we've got the same denominator on both lines. So they're going to cancel with each other, which gives us 5 out of 10. And if we want to write this as a decimal, it's going to be 0.5. So let's just quickly go have a look. What I'm going to hypothesize is that the top line here, which we've got is 5, that's going to be the number of red and small marbles that we had in the bag. And then the bottom line is basically going to correspond to the number of small marbles that we had in the bag in total. Okay, that's kind of what our condition is telling us. We're limiting the number of marbles that we have to pick from as just the ones that meet this condition. Okay, so scrolling back up to have a quick look at that. So what we can see is that the number of red and small marbles, it looks like 5. Again, we can check that from here. Small and red gives us 5. And then the total number of small marbles, I think you're going to find is 10. Okay, so it's like we've just limited ourselves to only be looking at what would happen if we had small marbles in the bag. What's the probability of them picking a red one? Alright, so the last thing that we have to look at is independence. So events A and B are independent if the conditional and unconditional probabilities are equal to each other. So we can write this again symbolically with our maths. So the probability of event A, if that's equal to the probability of A conditional on B, so this is the unconditional, this is the conditional, then if this is true, we have independence. Okay, so the two variables are independent of each other. However, the other case, so that's where the unconditional probability and the conditional probability are not equal to each other, then we have a dependent case. So A is dependent on what B actually is. So we're going to do an example where we're going to ask whether ball color and size are independent. So what we're going to do is pick out I guess one kind of example of an event. So I'm going to look at the probability of a ball being small, okay, and whether that's conditional on the different color that we have within the bag. So if we start with the probability of it being small, okay, that's our marginal case. So we can say that's going to be equal to the 10 from the margin divided by 14. And if you want, you can type this in as a decimal. It comes to 0.714. And then remember that if we're looking at this dependence, we need to look at the conditional probability then. So I want the probability of my ball being small conditional on the different colors. So if we start with red, okay, we should be able to work this out. Remember that you can write it with the other notation where it's the probability of being small and red, which is where we use the little intersection symbol, divided by the probability of it just being red. So small and red, we're looking for the intersect, so that's going to be the 5, divided by the total of 14. And the probability of it being red, just on its own, is going to be 6 out of 14. So these cancel with each other, and we get 5 out of 6. And this is about 0.833. Okay, now kind of at this point, I can already say that they're not really going to be independent because they're not going to be equal to each other. So the marginal probability of it being small is not equal to the probability of it being small conditional on it being red as well. If you want though, you could keep going. So the probability of it being small conditional on it being blue, again we can write it out. Looks like this. So the probability of small and blue comes from the intersection, which is 3 on 14, divided by the probability of it just being blue, which is going to be the 4 on 14. So the 14s cancel and it gets 3 on 4, which is 0.75. I'll go to the effort of doing the last one as well. So the probability of it being small dependent on it being green, or conditional on it being green. Again, you can write this out. Alright, so small and green is going to be the 2 from the intersection, divided by the probability of it just being green, which is 4 divided by 14. These cancel. 2 on 4 is 0.5. Okay, so from this, what we've got is that the probability of it being small does not equal the probability of it being small, conditional, and it also being red. This does not equal the probability of it small, conditional, and being blue, and also the green case as well. Alright, since we've got none of these things being equal, what we've ended up with is the second case here. Okay, so that means that these variables are variables are dependent. Okay, so ball color and size are dependent. And that would be my answer to that bit there. So that's all there is for this video, and I'll see you in another one.